Hello everyone and welcome back. This is the second part of our 10.2 video where we talk about summation notation. If there is anything out of chapter 10 that I think you should carry with you for the rest of your mathematical life, it is this. You can forget all about sequences, you can forget all the rules, but you need to know how to read and write things using this summation notation because it's going to come up pretty much every class here on out. So let's meet our friend, the sigma. That's this goofy looking thing right here. It is a capital Greek letter S, and the reason we use a Greek S is it stands for sum. It means we're going to add up a bunch of stuff. Hey, here's our friend the factorial, reminding us that that thing that looks like an E, it's not an E, it's an S. Capital Greek letter sigma looks like this. Lowercase Greek letter sigma looks something like that. That stands for standard deviation. Neither of them are the letter E. So, how do you interpret a sigma notation or a summation notation when you see it? Well, you think about it like a command. It is telling you, the reader, the writer, to do something. And what it's telling you to do is take a sequence and add up all the terms of the sequence. Maybe not all the terms. Some terms of the sequence. So, how do you interpret this? Well, this piece right here is the sequence. This piece is the sigma. That's telling you the command to add stuff up. And I said all the terms, not all the terms, but some of the terms. Well, what terms should we add? Those are going to be told to us by these letters up here and down there. So, when it says I equals 3, I is the part that's telling you what variable we're using. Usually you use I, you can use J's or K's. It's usually that sort of weird part of the alphabet. And this, 3, is called the lower limit of summation. And that is effectively telling you where to start. And the 5 on top is called the upper limit of summation. And it, surprise, surprise, is telling you where to stop adding. So, how do we work this out? Well, it's basically telling us to write the third through fifth terms of the sequence to I, and then add them up. So we go, and the index always goes up by 1 because it is part of a sequence. So the index is going up by 1 because that's what sequences do. So the third term, when I is 3, we do 2 times 3, and we get 6. When I is 4, we do 2 times 4, and this is not a very complicated sequence, and we get 8. And then we take 6 and add it to 8. So this is saying do 6 plus 8, but we don't stop yet because we haven't reached the upper limit of summation. So now we let I equal 5. We do 2 times 5, which is 10. We add that on to our sum. Now, I'm like, oh, this is really fun. Let me keep going. If I go to I equals 6, I get 12. Should I add 12 on here? No! Because 5 was the stop value. That was the upper limit of summation. So, this whole thing, we've made kind of a mess of our page now, but this whole thing is telling you to basically do 6 plus 8 plus 10. And then you should actually do it out. So 18. So that ends up being 24. And that's how summation notation works. It's a command that tells you what to add, where to start, and where to stop. And then you just have to do the thing that it's telling you to do. I'm just going to group all these examples together and let's write out some sums. So we have the sum from k equals 1 up to 8. So again, right, it doesn't have to be an I there. It's I usually for index, not imaginary, by the way, index. But sometimes we get tired of I, we want to use K or J or whatever. So in this case, we just kind of write out the terms. So you can make a little table. I'm actually going to make a table here. So we'll just make this row be K. And this can be K squared minus 1. Don't need 2 lines. This says start K at 1 and end K at 8. Okay, K squared minus 1, 1 squared minus 1 is 0, 2 squared minus 1 is 3, 9 minus 1, 16 minus 1, that'd be 24, 36, 47, 49 minus 1 is 48, 64 minus 1 is 63, forgot to take away 1, that's 35, I think that's right. And then the summation command is just saying take all of those and add them up. You could do that by hand. I'm going to just pause and do it on the calculator. Typing it all in, we get something like 196. By the way, if you have a relatively recent calculator, you can also do sigmas on here very easily as well. If you have an older one, the command is still there. It's just buried a little bit. You should probably just look it up. I mean, I can help you find it. But if you have a newer one, you're going to click alpha F2, which will pull up this hidden menu. This is the part that needs the new operating system. So if you don't have this menu now, then I can actually give you the OS update, but you should go get your operating system updated. Select that little sigma. Now you know what it is. And if you have your math type on, it'll set everything up here for you, including the variable. So I think we can type in, just have to find our K right here. So we're going to go from K equals 1. You can go over. It'll go to the next limit to 8, and we wanted to do K. Not like that. Oh, alpha K squared minus 1. Let's see what this comes up with. 196. Now, obviously, I need you to be able to do this by hand. Like, don't just trust your calculator and say, oh, I know how to type it in. I can just do everything. But it's a really nice way to check. And of course, if you have to add stuff up, casually, not for math class, it's a really good tool. So again, just to reiterate, that sigma is in alpha F2. Scroll down to 2. And if you have your pretty print math type all set to on, it'll come up like this. If you don't see that, come see me sometime during class and we can figure out how it works on your calculator. Most calculators do have some kind of sigma notation though. All right, let's do some other sigmas. So I now have a sum from I equals 1 to 5 of 4. And this is weird because it's not 4i, right? There's no I there at all. So you'd say, well, what is this? Is it just 0? Is there nothing? No. This is still the sequence, right? This is the sequence. It just turns out the sequence is 4, 4, 4, 4, 4, 4, forever. Forever. So in this case, if we make our little table, we say here's I and here's 4. We go I equals 1, 2, 3, 4, 5. Well, we just get 4, 4, 4, 4, 4. And then the sigma is the command to add all those up, plus, 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 plus. That's 4 times 5, or 20. So if you're missing a variable, it seems like it's going to be like a really difficult problem. It's actually the simplest kind of problem. It's kind of like the slope of a line with no slope almost. It's a constant function. You're just adding up the values times the number of terms you have, so 20. All right, here's a goofy one that I made up that we're not going to be able to find the sum, but I just want to write out the terms for it. And here's some things that might happen in sigma notation I wanted to show you in this problem. First, you don't have to start your index at 0 or at 1. You can start I anywhere you want. sometimes that really helps, like when you're dealing with exponents and you want to start with a 0 exponent, it might simplify the equation substantially to start with I equals 0 instead of having to do something fancy like I minus 1 in the power. Then up here, I'm saying n. That's saying that I don't know what number I want to stop at. I just want to stop at an unknown but finite n. So that's why I said we're not going to be able to find the sum, because we're just going to be, stopping and starting at an unknown but finite n. But everything else works the same way. We'll make a little table for I. We'll do 1/2 to the I. So in this case, our I starts at 0. So we'll do 0, 1, 2, 3. And here's where I'll skip a bunch of terms and then just say maybe n minus 1 and n. So those will be the terms of our sequence. So I to the when I is 0, -1/2 to the 0 is 1. Then when I is 1, -1/2 to the 1 is -1/2. Then it's +1/4 as you square it. -1/8. Skip, skip, skip. And then it's -1/2 to the n minus 1, -1/2 to the n. So how would I write this all out in a summation? Well, I'll write it down here where I have room. It would be something like 1 minus 1/2 plus 1/4 minus 1/8. We can do another term, plus 1/16. You can start to see the pattern. And then to show that you're adding but skipping some terms, you do plus, comma, ellipses, actually probably not a comma, plus, ellipses, plus, and then we're just going to do -1/2 to the n to show the pattern. And this is an example of an alternating series that is getting closer and closer to 0, but it's flipping back and forth. This would be kind of, if you graphed the terms, it'd be pretty cool. It would look something like this. That's it for each individual term, and then you might think, hey, I wonder if I add those up, is it going to make a single number, or is it just going to, keep growing in some way? I don't know. That's an interesting open question that I hope we'll address sometime during this section. Moving on, one thing you might get asked to do is write something as a summation notation. Maybe you're asked to compute this, and you're like, well, I don't want to add up all those numbers by hand, so you'd like to express it as a sigma so you can go chunk that thing into your calculator. This can be really difficult, and there's often not even a single one answer. Like there's infinitely many possibilities, which can make things harder, but it can also make it pretty fun. So when I'm writing things as a sum, I always try to think about like what's changing, where am I starting, where am I ending? Look for the changes, and like the more that you deal with sigmas, the easier this will get. This process of writing things in sigma notation. So I noticed that basically the base is changing, and I could say I bet the next term is 4 to the 2 and 5 to the 2. So I know the base is changing, but I also know this exponent is staying the same. I also notice that that's where we start, and 9 is where we stop. So start at 1 and stop at 9. So as a sigma, or a summation, well, we would write out our sigma. We would pick a variable. Let's use k. Let's start k at 1 and end k at 9. And then what are we doing to every number? Well, we're squaring it, so we could write it as k squared. You can always check by just going backwards. So if k is 1, then that's 1 squared. If k is 2, that'd be 2 squared. All the way up to k being 9, that'd be 9 squared. That seems to match and then they're added up because of the sigma. That seems to match what we thought. So now this is something you could easily type into your calculator and get the answer without having to add up all 10 terms or all 9 terms. Finally, to close, I want to talk about two really, really useful properties of summation. relating to how you can simplify something down. If it's really complicated, you have a really complicated sigma you're working with, it can really help to break it into multiple chunks. So, first property is about constant multiples. If you have the sum of something, number, a constant number multiplied to your variable, you can bring that number to the outside. So as long as it's multiplied to each term in the same way, it can't be changing, you can actually bring that out. And I have a specific example. We're not going to prove the whole thing, although it's pretty easy to prove. A specific example that'll show why this is true. So we're doing the sum from I equals 1 to 4 of 3i. So when I is 1, that'd be 3 times 1. I'm going to write, I know it's 3 times 1 is 3. I'm going to write it as 3 times 1 because I'm trying to show something. Plus 3 times 2 when I is 2, plus 3 times 3 when I is 3, plus 3 times 4 when I is 4. But notice that there's a 3 in all of those, so this could be written as 3 times 1 plus 2 plus 3 plus 4. Right, just bring the 3 out. So the fact that you can bring a 3 out of addition using the distributive property is what allows us to bring the constant terms out of summation. It's basically factoring. So then I could write this, well, this is 3, and then 1 plus 2 plus 3 plus 4, well, that's the sum from I equals 1 to 4 of not 3i, but just I. And notice what I've done. We brought the 3 from the inside to the outside. And that'd be true no matter what, as long as it's a constant multiple, you can bring those to the outside. It usually substantially simplifies the inside of your sigma. Here's another thing you can do. If you have a sum of a sum, so we have two things added together, and then in our sequence, and then we've been commanded to add those all up, you can kind of distribute the sigma to each of those terms. Probably distributes the wrong word, but it effectively operates in a similar way. You can add each of those things up separately. And again, I want to prove that and demonstrate it with the sum from I equals 1 to 4 of 2 plus I. Again, this is not I, the imaginary number. This is I, the index of summation, just in case it was confusing. It is a little messy. So when I is 1, this is 2 plus 1. When I is 2, so that's the 2 plus 1 here. Then I'm going to add the next term, which is 2 plus 2 here. Why don't we do this? The next term would be 2 plus 3. The next term would be 2 plus 4. And then I would stop because we've reached the upper limit of summation. Well, those parentheses, other than showing what term we're on, are completely unnecessary. And addition is commutative and associative. So I could write this as 2 plus 2 plus 2 plus 2 associated with 1 plus 2 plus 3 plus 4. Just regrouping and moving things around. And it's all addition, so that's all okay. Well, what is this? This is one of those goofy constant sums. The sum from I equals 1 to 4 of 2. And this is what we saw above, the sum from I equals 1 to 4 of I. And what have we done? We separated out a complicated sum into two much smaller sums. And this would be something like if you had to evaluate this by hand, I would definitely do this because you can easily do that term, right? It's just 8. And then you only have to do this much simpler term. So I really recommend it, especially when the numbers get big, using these two properties of breaking up addition and factoring out constant multiples. So helpful when working with sigma notation. So just to close and recap, sigma notation is the most important notation you're going to learn in this section. It is so useful all the time, and there's a lot of other things in math that have lower and upper limits that operate in a similar way. You're going to see a lot of that in calc next year. So all the time you spend learning sigma notation right now is totally worth it. It's a command that's telling you to add some stuff up. Everything else is just telling you what to add and where to start and where to stop. Whenever you see that sigma, know that you're going to be adding some terms together. Let me know what questions you have. Make sure you do your math homework, and I'll see you all next time.